In section 8.2, we're looking at rational exponents. Our objectives are to use exponential notation for nth roots, define and use expressions of the form a to the m divided by n power, convert between radicals and rational exponents, and use the rules for exponents with rational exponents. Here are some formulas that we use when we're dealing with rational exponents. A to the 1 over n power can be written as the nth root of a. A raised to the m divided by n power can be written as the nth root of a to the m. A to the m divided by n power can also be written as the quantity of a to the m raised to the 1 over n power. And a to the m divided by n can be written as the nth root of a, all raised to the m power. So in keeping these formulas in mind, the part that's in the denominator of the exponent is the index of the radical. Again, the part that's in the denominator is the index of the radical. Let's evaluate exponents of the form a raised to the 1 over n power. The 27 to the 1/3 power can be written as the third root of 27, and we're looking for the number raised to the power of 3 that gives you 27. Since 27 is 3 to the 3rd power, and we want to raise that to the 1/3 power, we can simplify this 27 to the 1/3 power as the third root of 27, which is equal to 3. 64 to the 1/2 power can be written as a radical. The 1/2 power would indicate that the index is 2, so this can be written as simply the square root of 64, and the square root of 64 is 8. Now, negative 625 raised to the 1/4 power can be written as negative 1 times 625 to the 1/4 power. And that 1/4 power can then be written as negative 1 times the 4th root of 625. Now 625 can be written as 5 to the 4th power. So we can simplify this radical expression as negative 1 times 5, which is equal to negative 5. Now the last example looks very much like the first. However, we have the quantity negative 625 in parentheses. So we can think of this as the 4th root of the entire quantity, negative 625. Now we say that since the index is an even number and the number under the radical, the radicand, is negative, we have to say that this is not a real number. Remember that for even indexes, for radicals, the radicand must be positive. So for this one, we could say that the 4th root of negative 625 is not a real number. Now we can take the 5th root of a negative number, so let's rewrite this example as the 5th root of negative 243. We want to find the number raised to the 5th power that will give you negative 243. So recall that negative 243 is the same thing as negative 3 times negative 3 times negative 3, 5 times, or negative 3 to the 5th power. So the 5th root of negative 243 is negative 3. Let's do the fraction 4 over 25, all raised to the 1/2 power. The 1/2 power can be written as the square root of 4 over 25. And we can then write this as the square root of the numerator over the square root of the denominator. And the square root of 4 is 2, and the square root of 25 is 5. So this expression is simplified to 2/5. Now we're looking at evaluating exponentials of the form a raised to the m divided by n power. In example A, we have 25 raised to the 3/2 power. 25 to the 3/2 power can be written as the square root of 25 to the 3rd power. We could also write, again, that index is what the number in the denominator is the index, and since that is 2, we don't necessarily need to write down that it's a square root by indicating the index of 2. That's understood. So we can also write this as the square root of 25 all raised to the 3rd power. And we know that the square root of 25 is 5. So this can be written as 5 to the 3rd power, which is 125. Let's look at example B. B is 32 raised to the 2/5 power. So we can write this as the 5th root of 32 to the 2nd power. We can evaluate the 5th root first and then square the result. So let's write it as the 5th root of 32 and then raise that quantity to the 2nd power. And the 5th root of 32 is 2. Recall that 32 can be written as 2 to the 5th power. So the 5th root of 32 is 2, all raised to the 2nd power, and that simplifies to 4. Example C, negative 27 to the 4/3 power. Let's think of this negative out in front. Because it's not in parentheses, that's the same thing as negative 1 times 27 to the 4/3 power. 27 to the 4/3 power can be written as the cubed root of 27 to the 4th power. So let's evaluate the cubed root of 27 first and then raise it to the 4th power, and then finally multiply the result by negative 1. So it's going to be negative 1 times, we'll do the cubed root of 27, and then we'll raise that to the 4th power. So that's going to be negative 1. The cubed root of 27 is 3. Recall that 27 is the same thing as 3 to the 3rd power, so the cubed root of 27 is 3. So this is going to be negative 1 times 3, the cubed root of 27, all raised to the 4th power. And if we do the exponent first, 3 to the 4th power is 81. So we'll get negative 1 times 81, and the result is negative 81. Example D, negative 64, the quantity raised to the 2/3 power, can be written as the cubed root of negative 64 to the 2nd power. We can do the cubed root of negative 64 first and then raise that result to the 2nd power. The cubed root of negative 64, find that quantity and then raise the result to the 2nd power. Now the cubed root of negative 64 is negative 4. Recall that negative 64 can be written as negative 4 to the 3rd power. So the cubed root of negative 64 is negative 4, and then we're going to square that quantity to get our final answer. Negative 4 quantity squared is 16. Okay, example E, we have in parentheses negative 16 raised to the 3/2 power. If we rewrite this using a radical, the index is the denominator, so it's the square root of negative 16 to the 3rd power. Now, caution here, we need to observe that if the index is an even number, the radicand cannot be negative. And when you take negative 16, raise it to an odd power, that result is going to be negative. So this is not a real number. And again, the reason why it's not a real number is the rational exponent, 3 divided by 2, is written as the square root of that quantity to the third power. Since the square root is an even index, the radicand cannot be negative. So the result here is not a real number. Let's look at evaluating exponentials with negative rational exponents. One way to work with negative exponents is to make the exponent positive by moving it from the numerator to the denominator. So let's write this expression as a fraction, where we can think of this as 1 times this quantity to the negative 4/5 power. So we'll keep the 1 in the numerator, but the 32 base we're going to write in the denominator. And when you do that, that negative exponent becomes positive. Now we can write this as 1 over the 5th root of 32 to the 4th. We can write this as the 5th root of 32, find that result, and then raise it to the 4th power. Now recall that 2 to the 5th power is equal to 32. So the 5th root of 32 is 2. So this can be written as 1 over 2 to the 4th power, and 2 to the 4th power is 16. So we can write our final answer as 1 over 16. For example B, we have the fraction 8 over 27 all raised to the negative 4/3 power. We could make this exponent positive by writing the reciprocal of 8 over 27. So let's write this as 27 over 8. And in doing so, we can make this negative 4/3 exponent a positive 4/3. Now let's rewrite it as a radical. That cubed, that 1/3 power, or the 3 in the denominator exponent, ends up being the cubed root of 27 over 8, and then we can raise the entire quantity to the 4th power. Further, we can take the cubed root of the numerator and the cubed root of the denominator. We can write this as the cubed root of 27 divided by the cubed root of 8, that entire quantity raised to the 4th power. And the cubed root of 27 is 3, and the cubed root of 8 is 2. Now we can raise this entire quantity to the 4th power. We can raise 3 to the 4th power divided by 2 to the 4th power. And 3 to the 4th power is 81, and 2 to the 4th power is 16. So we can write our final answer as the simplified rational expression 81 over 16. Caution, be careful to distinguish between exponential expressions like the following. 16 to the 1/4, the negative 1/4 power, that equals 1/2. Again, recall that 16 to the 1/4 to the negative 1/4 power can be written as a fraction 1 over 16 to the 1/4 power. And then further, this can be written as 1 over the 4th root of 16. And since 2 to the 4th power is 16, this result is 1/2. Now, notice that that is different than negative 16 to the 1/4 power, which equals negative 2. So if we were to work through that, the negative 16 to the 1/4 power, that's the same thing as a negative 1 times 16 to the 1/4 power. And then we can write this as that negative 1 times the 4th root of 16. And then we get negative 1 times the 4th root of 16, which is 2. So our result is negative 2. Notice the difference here, that we get negative 2 when we are evaluating negative 16 to the 1/4 compared to our 1/2 that we get when we're evaluating 16 to the negative 1/4. Notice the problems look similar, But in the first example, the negative is in the exponent, and the second example, the negative is out in front. And then, looking at this last example, here we have negative 16 to the negative 1/4 power, and that equals negative 1/2. A negative exponent does not necessarily lead to a negative result. Negative exponents lead to reciprocals, which may be positive. Let's convert between rational exponents and radicals. 15 to the 1/2 power can be written as a radical, with a radical. And that is the same thing as the square root of 15. That denominator of the exponent is the index. And in this case, since the index is 2, we don't necessarily need to write that 2. A basic square root is automatically assumed that the index is 2. So that's how we can write our answer as a radical. For part B, we can write 10 to the 5/6 power as a radical, and the denominator of the exponent is the index of the radical. So we can write this as the 6th root of the radicand, which is 10 to the 5th power. For example C, we have 4 times n to the 2/3 power. Now n to the base 2 is raised to the 2/3 power. The 4 is a coefficient. We're going to leave the 4 out in front so that we can write this as 4 times the cubed root of n to the 2nd. We can write it in this way, 4 times the cubed root of n to the 2nd. We could also write this as 4 times the cubed root of n, the entire quantity raised to the 2nd power. Let's look at example D, 7h to the 3/4 minus 2h in parentheses to the 2/5 power. The 7 is the coefficient. That's going to stay out in front. The h is the only base raised to the 3/4 power, so we write that as the 4th root of h to the 3rd power. Now the second term is minus the quantity 2h, so the 2h is the entire base raised to the 2/5 power. So we can write this as the 5th root of the quantity 2h raised to the 2nd power. And we can leave our answer in this form. Here we're just practicing converting between rational exponents and radicals. Example E, g to the negative 4/5. This negative exponent can be written as a positive exponent by writing it as a fraction. So our numerator is a 1 and the denominator is g to the positive 4/5 exponent. Now we can convert that positive exponent into a radical and write the result as the 5th root of g to the 4th. Remember, the denominator of the fraction rational exponent ends up being the index of the radical. Let's find the square root of 33. Now let's go from the radical form to the exponential form. We can write this as a radical 33 raised to the exponent of 1/2. The cubed root of 7 to the 6th can be written as 7 to the 6th power raised to the 1/3 power. You can also write this as a power to a power. You can multiply those powers together. 6 times 1/3, which is 6/3, 6 times 1/3, and then that can be simplified to 7 to the 2nd power, and then finally you could go further and write this as 49. Let's look at h, the 5th root of m to the 5th power. The 5th root becomes the denominator of the exponent. So we can write this as m to the 5th raised to the 1/5 power. And then we have power to a power. We can multiply those together and write this as m to the 5 times 1/5, which is 5/5, which is 1. So this can be simplified to simply m. Let's look at the rules for rational exponents. Let r and s be rational numbers for all numbers a and b for which the indicated expression exists. we have a raised to the r power times a raised to the s power equals a to the r plus s. This is an example of the product rule for exponents. If the bases are the same, then you add those exponents together. We have a to a negative r power can be written using a positive exponent, 1 over a to the r. A to the r divided by a to the s, this is an example of the quotient rule for exponents. If the bases are the same, a, and the exponents are r and s, and you're dividing, then the quotient rule says that you can subtract those exponents. Now, the next example we have here, that the fraction raised to a negative exponent, you can write the exponent as a positive exponent as long as you write the reciprocal of the fraction, a over b. Now, we have the power rule for exponents. When you have a base a raised to a power of s raised to another power of s, the power rule says you can multiply those exponents together. Now, some of the other rules that we used with exponents in previous sections apply as well to rational exponents. If we have the quantity ab to the r, you can write that as a to the r times b to the r. You have the fraction a over b to the r can be written as a over r times b to the r. And a to the negative r exponent can be written as the reciprocal of a, 1 over a raised to that positive exponent of r. Example 5, we have 6 to the 3/4 times 6 to the 1/2 power. Since the base 6's are the same and we have a product here, we apply the product rule where we're taking the base 6 and raising it to the 3/4 plus 1/2 power. Let's add 3/4 and 1/2 together so that we get 6 to the 5 over 4. So we can leave our answer in this form here. For example, part B, 3 raised to the 2/3 power divided by 3 raised to the 5/6 power. Since those bases are the same, then we are going to use the quotient rule and subtract the exponents. So that's going to be equal to 3 raised to the 2/3 minus 5/6 power, or exponent. By subtracting those fractions, we get the base is 3, 2/3 minus 5/6. You can get a common denominator here of 6. So that's the same thing as 4/6 minus 5 over 6. And 4/6 minus 5/6 is negative 1/6. Now we can write our answer using a positive exponent. So 3 raised to the negative 1/6 power is the same thing as 1 over 3 to the 1/6 power. All right, let's simplify part C of this problem. That we have the entire quantity m to the 1/4 times n to the negative 6, all divided by m to the negative 8 and n to the 2/3 power. This entire fraction is raised to the negative 3/4 power. So what we can do first is we can distribute that exponent with all of the terms that are in the fraction. When we do that, we get m to the 1/4 power, all raised to the negative 3/4 power. And then we get n to the negative 6, all raised to the negative 3/4 power. So we're distributing that exponent with all the terms that are in the numerator as well as all the terms that are in the denominator. Then we take in the denominator m to the negative 8, we raise that to the negative 3/4 power, and then n to the 2/3, we raise that to the negative 3/4 power. Now let's simplify each of the parts of the fraction here. Using the power rule, we have the power of 1/4 raised to the negative 3/4. That we can simplify. 1/4 times negative 3/4 is negative 3 over 16. Now let's use the power rule with the n to the negative 6 raised to the negative 3/4 power. Now negative 6 times negative 3/4 can be simplified to get negative n to the 9 over 2 exponent. In the denominator, m to the negative 8 to the negative 3/4 power, again, using the power rule. We can simplify this because 4 goes into 8 2 times, and then when we multiply the exponents together, n to the negative 2 times negative 3 will give us m to the 6th power. And then we multiply the exponents for the denominator, n to the 2/3 raised to the negative 3/4 power. We can multiply 2/3 times negative 3/4. This does simplify. So 2/3 times negative 3/4 ends up giving us n to the negative 1/2 power. Now that we've taken care of that exponent of negative 3/4, we can apply the quotient rule. Notice that we have an m to the negative 3/16 in the numerator and an m to the 6th in the denominator. We can write this as, using the quotient rule, we subtract the exponents. So we can write this as m's the base, negative 3/16 minus 6. Notice now we are subtracting the exponents. And then the same thing with the n's. N in the numerator and n in the denominator have the same bases, so we're going to subtract those exponents using the quotient rule, 9/2 minus a negative 1/2. By simplifying those exponents, we get m raised to the negative 3/16 minus 6. You can add those together, or subtract actually, and get raised to the negative 99 over 16 power. Now you can use a calculator, scientific calculator with a fraction. You can simplify negative 3 over 16 minus 6. You'll get a decimal, but you want to write your answers as fractions in reduced form. So we get m to the negative 99 over 16 times, and if we subtract 9/2 minus a negative 1/2 and simplify, we get n to the 5th power. Now we're very close to the final answer. In our final answer, we want to write only positive exponents. So that n to the 5th is a positive exponent. We're going to leave that as n to the 5th in the numerator. But this negative exponent for m, we can write as a positive exponent. So we can write this as m to the 99 over 16 in the denominator. So that would be our final answer. Simplified, we use the power rule as well as the quotient rule. For part D, let's simplify by multiplying the monomial x to the 3/5 times the binomial in the parentheses. We use the distributive property. We multiply each term in the parentheses by the x to the 3/5 power. So we'll have x to the 3/5 times x to the negative 1/2 power minus x to the 3/5 times x to the 3/4 power. Now we can apply the product rule. When you're multiplying and the bases are the same, then you can add those exponents together. We're adding the 3/5 and the negative 1/2. So that's going to look like this. We have the bases are the same, and then we would write this as 3/5 plus a negative 1/2. And the same thing for the second term. The bases x's are the same, so we are going to add those exponents together, and that's going to look like the base x raised to the 3/5 plus 3/4 power. Now add those exponents, and we get 3/5 plus negative 1/2, which is 1/10. And 3/5 plus 3/4 is 27 over 20. Again, you can use a calculator to add those fractions together and simplify. Otherwise, you do want to get the least common denominator. For example, if you multiplied by 2 in the numerator and the denominator, and by 5 in the numerator and the denominator, you will get 6 plus a negative 5, which gives you 1 over 10. And similarly with the second term. Now we have this binomial, and that's going to be our final answer in simplified form, x to the 1/10 minus x to the 27 over 20. All right, let's simplify this radical expression by first converting to rational exponents and then applying either the product or quotient or power rule for exponents. So the fourth root of a to the third can be written as the a raised to the 3 over 4 power, and the cubed root of a squared can be written as a to the 2 over 3 power. Now notice that the bases are the same. Both have a base of a, and we can multiply the multiplying using the product rule means we're going to add those exponents together. So our result here is going to be a raised to the 3/4 plus 2/3 power. Then we can add those exponents together. 3/4 plus 2/3 is 17 over 12. So we can leave our answer in this form, as well as writing this as the 12th root of a to the 17th power. For part B, we have the fourth root of c divided by the square root of c to the third. Let's convert to rational exponent form so that we end up with, in the numerator, the fourth root of c is written as c to the 1/4 power, and the square root of c to the third can be written as c to the 3/2 power. Since the bases are the same, both have a base of c, what we can do is we can use the quotient rule and subtract those exponents. So this will look like c to the 1/4 minus 3/2 exponent. Let's simplify the exponent to get c to the 1/4 minus 3/2, which is negative 5/4. And then write our final answer using a positive exponent. We can write this as a fraction, 1 over c to the 5/4 power. All right, let's simplify this radical expression. We have the fifth root of the cubed root of x squared. Let's write this index of 5 as a 1/5 exponent. So starting with the fifth power, the fifth root, of the cubed root of x squared is the same thing as the cubed root of x squared raised to the 1/5 power. Now the cubed root, going further, the cubed root of x squared can be written as x to the 2/3 power, along with that 1/5 power. Now we can apply the power rule for exponents, since we have the base x raised to the 2/3 power, which is raised to the 1/5 power. We can use the power rule for exponents, and when we do that, we are going to multiply those exponents together. So our base is x raised to the 2/3 times 1/5 power, and that will simplify to x to the 2/15 power.